For the final set of slides and video lecture on code optimization, we're going to do a broad introduction to the vast area of code optimization. We can't really do an in-depth study in code optimization in the time we have left, but I want to give you a broad overview of this topic and some pointers as to how you can learn more about it by looking up various textbooks and other sources. Code optimization is a big area of work in compilers. The first thing to realize about code optimization is that there is no fully optimizing compiler. Let's call such a compiler, if it exists, O, and we can show that such a fully optimizing compiler cannot exist. So optimal often means the best, right? It's always the best thing you can do is optimal. So when we say code optimization, we're trying to reach that goal, and we are guaranteed never to reach the optimal code for any given program. So let's first see why there is no fully optimizing compiler. Let's assume that it exists. Let's say that we define code optimization in a very straightforward way. It takes a program P and produces an output opt of P. So it's a new program, which is the smallest possible. So it takes a large program and has a lot of instructions and then shrinks it down into the smallest possible equivalent program opt of P. So we start with P, we end up with opt of P. Now, if such a optimizer existed, we have this program O. So O, of course, is also a program which takes an input program and produces an output. Imagine a program Q that produces no output and never terminates. It's likely that Q has some kind of bug and goes into an infinite loop. If it's a defective program like that, then the smallest optimal program that's equivalent to Q would be just something that immediately goes into an infinite loop. That is the smallest program that produces no output and never terminates. If I want to check whether a program P never terminates on some inputs, all I have to do is to check whether the opt of P of I is equivalent to this opt of Q. So notice that opt of Q is a program that never stops. It always goes into an infinite loop. So if I can use that by saying, well, if it's optimal on a certain input I, P goes into an infinite loop, then the opt of Pi should also look like this, which is the program that's the smallest possible program that never terminates. This optimizer now has solved the halting problem, which is something that Alan Turing worked on and showed that it's impossible to write a program. It's impossible to write down a Turing machine or any other kind of computational device that will take an input program P on a certain input I and then tell you, does it terminate, telling you that that program has a bug in it and on that input is never going to terminate. So the halting problem has been proven to be impossible. So therefore, this opt of Q is impossible to get, and there can't be a fully optimizing compiler O. That doesn't mean you can't do code optimization. Of course you can, but you cannot produce the best possible optimizer ever, because if you do, you'll solve the halting problem. This is called the full employment theorem for compiler writers by Rice, 1953, a proof that goes through the halting problem and shows why these kinds of programs can't exist, why you can't have a fully optimizing compiler. So this is a bit tongue-in-cheek to call the full employment theorem. That means that there always will be a job for a compiler writer, because nobody can say this is the best optimizer ever. A compiler writer will always have a job trying to make a better code optimizer. In code optimization, we'll go through the following topics. These are mostly introductory. These are supposed to give you an introduction to these topics. They don't go fully in depth in any of these, but they're useful to know as a compiler writer, like what are the different optimization topics out there, how they would be integrated into the optimizer. For our purposes, LLVM has implemented a large number of optimization steps already, and Homework 4 goes through and points out optionally what you can look at in terms of optimization optimization of your of the code that comes out of LLVM for your decaf programs. So the first thing we'll look at is non-optimizations. We look at correctness and make sure that optimizations don't change the meaning of the program. This is quite hard. You'll find that aggressive optimizers often do change the meaning of the program and sometimes introduce crashes when none existed in the non-optimized version. We want to avoid that as much as possible. There are different types of optimization, so we'll cover local optimization and so-called peephole optimization, where you look at a small portion of the code to do optimization. We'll briefly talk about global data flow analysis, which looks at the entire running program to figure out how to optimize it. But this is a huge topic of research. It has been for decades, and really it hasn't been that effective in the long run. And a lot of local optimization and peephole optimization produces very good results. And global data flow analysis is done for some things. As we've seen, we've done some data flow analysis for register allocation, as we saw in the register allocation lectures. In terms of making very optimal code, it's a lot of work to do global data flow analysis. I guess not that much benefit. Thing that does work is if we have our intermediate representation in static single assignment form, it turns out there's a lot of optimizations we can apply to SSA form that result in much more optimal code being generated and therefore much more optimal assembly code being generated at the end. And finally, we'll talk about what Amdahl's law is and what that implies for code optimization. First, let's cover non-optimizations. So there are certain times you see in people's code, they will take a variable assignment like this. If that variable has to be checked against a value, they might use the fact that enum have 0, 1, use that value. Instead of explicitly checking it, take this and put it inside the if statement. Now, often programmers do this kind of thing because it reduces the number of lines of code in the program text. But if you are experienced compiler writers at the end of this course, and you know that in terms of the intermediate representation and definitely in the assembly that gets produced, either one of these will produce the same output. Like one is not faster than the other or more optimal. So these are what I would call non-optimizations. And there's a lot of non-optimizations that are done by programmers who don't quite know how a compiler works. There's different types of optimizations. There's high-level optimizations like function inlining or loop unrolling. So if you want to avoid some overhead, like the overhead of calling a function, you need to set up the stack, you need to set up the activation record, etc. By inlining that function, you're increasing the size of the program, but you're avoiding the overhead of calling that function. Another trick is loop unrolling, where instead of having a goto statement or a conditional, you can unroll the loop to avoid calling the conditional that happens at the beginning or at the end of every loop, and unroll it for a certain number of steps. If you are sure that it's a fairly long-running loop that runs over hundreds or thousands of iterations, then you can unroll it into groups of 100 or groups of 1,000. There are some machine-dependent optimizations that are called peephole optimizations or instruction scheduling, where groups of instructions can be replaced with a more powerful instruction. But these are machine-dependent. And then there are local transformations that you can do within a basic block to replace some groups of instructions with other instructions that accomplish the same thing. So we might be taking 3 instructions and then rephrasing it as 2 instructions, or maybe even 1 instruction. And sometimes even eliminating it so that there is nothing there. So there's no instructions at all because these sequence of instructions are essentially redundant. So these local optimizations take a look at a basic block and then try to optimize the code inside that basic block. And this is quite helpful because sometimes the basic block that you're optimizing is in the middle of some inner loop. And so by reducing the number of instructions in here, at the runtime, you are really making the program more efficient, therefore more optimal in terms of running time. So let's look at global optimizations briefly. Global optimization or data flow analysis takes the entire program in fact, even multiple programs that call each other, and looks at how to globally optimize this code. Essentially, we're going across basic blocks here, and it could be within one function or procedure, which is called intra-procedural, or the entire program across all the functions it has. It's called interprocedural. And finally, you can do alias analysis to track the pointers in a more global way across the entire program to make sure that the access of data is optimized as well. The most important thing, as we've seen all along, is to maintain correctness. So when we write a compiler, our duty as a compiler writer is that we should not invent something that isn't there in the program. We should maintain the fact that the programmer thinks that it's correct in a certain way, it should be written down and specified, then we should obey that contract. Here's an example where this conditional is always going to, it's never going to execute that code. Right? We assume that it's never going to do that because of the way short-circuiting works. And if we say that our compiler does produce short-circuit evaluations that are going to skip over this piece of code over here, then when I compile this program, this actually is, it looks like a hodgepodge of C and decaf. It should really say func main int. To be a valid decaf program. But the point is that it should not execute this because we are expecting our compiler to produce short circuit evaluations for conditionals like this. As a result, it should produce, when I do a print int here, it should print out 3. It shouldn't print a divide by 0 exception. It shouldn't produce that, even though there is a divide by 0 exception in this code here. The expectation is that it will not execute that instruction. However, this is not as straightforward as it might seem, because right after a conditional evaluation like this statement, where it's evaluating a conditional is often a slower instruction to execute. And while the CPU goes and executes a conditional, it can actually execute other instructions at the same time while it's calling out to the conditional. And this is called a branch delay slot. Essentially, while it's executing the conditional statement, it has some cycles left in the CPU to execute extra instructions. So this is often called a branch delay. Because there is a delay in executing the conditional, we can execute some instruction. So you might take this instruction in particular and evaluate it just in case the conditional comes out to be true before you even execute the conditional. And then depending on what the conditional returned, you could use it or throw it out. And this is also what is done in branch prediction, where in branch prediction you predict which go-to is it going to be, this one or this one. And if it picks this one, then you picked correct because it's going to come back as false. And you already have executed the load of 3 into the location X. So branch prediction can help you take advantage of the delay in a branch, in a conditional statement, and execute some instructions while you're waiting for it to finish. The problem here is if the branch prediction is incorrect, you will end up executing this statement, which gives you a divide by 0 exception. So your code optimizer shouldn't do that because it violates the contract for saying that we're short-circuiting this evaluation. It's tricky. So we want the branch prediction to work, and if it does work, then we can make our code run faster because we've already executed that instruction before we need it, essentially. It's already ready for us. A similar thing happens when you have a load from memory or a store from memory. It's called a load delay slot. So when I have a load T1 and then we have some address in memory, it has to go to memory, fetch that piece of memory, bring it back and store it into the T1 location. This, as you can imagine, takes time, and so while it's doing this load, it can execute the subsequent instructions before the load is actually complete, as long as these instructions don't use T1. So if they don't use T1, then we can go ahead and execute them. the resulting program would still be correct, but we've taken advantage of this time delay that happens when you do a load. So this is often called a load delay slot. So it's a slot of time where you can do work in the CPU while it's doing other things like going to memory or executing a conditional statement, etc. So, but it's very carefully done because we want to maintain correctness. So it's often the case that it will be incorrect to use these delay slots in some cases, and so the compiler has to be very careful about when it uses it and when it doesn't. As we've seen recently, last year, there was, even in the CPU implementations, they have branch prediction, help to do branch prediction, etc. in the CPU. So in x86 chips, there was branch prediction that was exploited to introduce security vulnerabilities. Malicious attacker could use the delay slots in order to execute malicious instructions, essentially. So there was a definite breakdown in maintaining correctness in the pursuit of faster execution. So you have to be always vigilant about these things. People optimization is a commonly used simple code optimization technique. Actually, it's a set of techniques that altogether we can call people optimization. Essentially, are looking at the sequence of instructions that are inside a basic block and then doing some kind of optimization to make this code more optimal. So we're just going to go through different examples of what is commonly done inside people optimization. The first thing is redundant instruction elimination. If two instructions perform the same function and are in the same block, then we remove one of them because it's already being done by this other instruction. Here are some examples of that. You can have redundant loads or stores. This can arise as a result the way that the code is generated. So you might end up with two load instructions in the same basic block, and they're both loading it in the same location. So you can get rid of the earlier one because the second one is going to overwrite it anyway. We can also remove unreachable code, and this can happen because there might be a basic block you set up, and this basic block is in fact all of the instructions in this basic block are unreachable. There's no way in this program to reach that basic block, and so you might as well remove that basic block altogether and not generate the code for it. Another way you can do sort of local optimization is flow control optimization. In this case, you have to go to L1. When you get there, all you do is immediately go to a different location. And again, this can be a byproduct of various ways of doing code generation. And at this point, you can take these redundant go-to statements and just keep a go to L2 over here instead of an L1. We have to keep the code here just in case L1 other targets, there's another go-to function somewhere else that can generate a go to L1. We need to keep that around, but at least we don't have to do two go-to statements in this line. The other thing you can do is algebraic simplification, and I'll show you some examples of that. If you're doing some arithmetic operations or Boolean operations, you can in some cases simplify it into a simpler form, and then that's a more optimal code to run. You can do reduction in strength. So essentially, you can use faster instructions whenever possible. If you're doing exponentiation, for example, maybe there is a machine, in that particular machine, there might be a faster way to do that exponentiation operation instead of calling a repeated multiplier. There are various machine idioms one can use. For example, in x86, there are various ways to parallelize code using AVX instructions like vector operations, etc. So using those are what we would call machine idioms, where the chipset has support for some kind of specialized processing, either vector processing or matrix multiplication, whatever. And finally, filling delay slots, which we already talked about. So when you have load delays, branch delays, each of these gives an opportunity to add instructions or reorder instructions and get more work done in less time. So that's what the code optimizer is always looking for. But as we saw, there are some cases where filling delay slots can lead to bad code, incorrect code. But most of the time, it is definitely used a lot in modern code optimization because the opportunity is there to start executing instructions while the CPU is busy doing something else, or while a different part of the computer is, loading from memory, etc. So that time can be well used in executing extra instructions. So does lead to more optimal code. Constant folding and propagation are simple ideas, but they are very powerful, as we'll see in some examples later on. Constant folding computes expressions with known values at compile time. If you have, it might look like a variable. I'm using a variable x. Because of the static analysis, we can tell that x is actually going to be assigned a value 0. And so instead of using x, we can replace x with 0 everywhere. And sometimes that can lead to more efficient code. Constant propagation is the same idea, where a constant is assigned to a variable. We assign that variable with a constant. And if the expression and a constant are known to have a certain value, we can propagate this value across. So essentially, somewhere else, if I have y is equal to x, then x we know is replaced with a 0. We can replace y with a 0 as well. So that's what we mean by propagation, right? We take the values and we propagate them to other values. Here's an example of copy propagation, where instead of doing this d plus e, I assign a variable t in both of these branches to d plus e, so I can reuse that value t here. So it's not just for constants, but you can also propagate copies of the same value. So we can see that this is a good transformation. It doesn't change the answers. There are many other transformations one can take, like structure preserving transformations. We saw some of those with respect to goto statements, or rearranging the code in such a way that it preserves the structure but makes the code a little bit more optimal in terms of number of instructions. We can also do common sub-expression elimination. In this case, if I have d is equal to a minus d, which I know has been pre-computed and stored in this variable b here, then I can, instead of doing this subtraction again and wasting another instruction, I can reuse that value that was computed. So as long as the value is computed and we know that a and d have not changed since then, so if we know that it hasn't changed the values of a and d, then we can simply replace this a minus d with the value for b. Another kind of transformation we can do is dead code elimination. So you could propagate a constant. So you can do constant folding and then copy propagation of that constant. So a good example is, often we have debug flags. So if debug, then do this function. Well, debug might be set as a constant at the beginning of the program. We might be actually compiling it with the debug flag set to false, or compiling it with the debug flag set to true. If it's set to false, we can actually propagate that value into this conditional. Since this code is never going to be reached anymore, we can remove this code altogether, this call to the function f altogether. So the code would never even exist in the output. We would essentially remove the code associated with that entire conditional if statement is removed. The other way you could use temporaries is, if I have a sequence of instructions like that, we have x is assigned a value of t3, it might be helpful to use the same temporary variable, assign it to t4. This might have a beneficial effect in future code optimization steps. We can rename temporary variables. So t1 change to t2, as long as these variables are unique. So sometimes in SSA form, it doesn't really matter if you change it to T1 or T2. We just have to keep track of it. It might or might not be beneficial to rename these temporary variables. Sometimes it can lead to sharing of values and increase the opportunities to do copy propagation. In SSA form, this is really not all that useful. There could also be interchange of statements. So I can take this statement, assignment T1 and assignment to T2, and switch the order of the statements here. And this can be combined with branch delay slots or load delay slots. To often execute the instructions in a different order can help, because you're doing this work in the time when the CPU is idle. The algebraic transformations, where you know that because you did some constant folding and copy propagation, maybe you know that this is going to end up being a 0, then we can eliminate this plus and just replace it with a plus 0 can be replaced with an a. D times 1 can completely be eliminated because essentially I'm not changing the value of d. If it was e is assigned to d times 1, then I would keep it, except I would take away this multiplication. The other thing one can do is reduce the strength. So you can, if I know that I am doing an exponentiation of a raised to 2, I can replace it with multiplication. That makes it a lot more efficient to calculate a single multiplication than to call an exponentiation or power function for this statement. Let's apply all of these ideas that we just learned about in terms of local optimization or people optimization, but let's apply it to intermediate code that's in SSA form, and we can see SSA form actually provides us with more benefits in code optimization as well. SSA form contains statements and basic blocks and variables, locations. So whenever I say variables, I also mean locations. Locations are places we can put things or places we can go to, etc. Dead code elimination can be done if there's a variable v with no uses, so it's never used, and the definition of v has no side effects. So whenever we define that v, it doesn't have any extra side effect like loading into memory or any other side effect for any other variable. We can, if such a variable exists, it's not used, then we can just delete that statement defining v. In terms of a phi function, if I have no definition for x and no definition for y, then I can just eliminate this entire statement because I'm not going to be using it. Essentially, if I wanted to use z somewhere and x and y don't have any definitions, then z should not be used either. Right? Otherwise, x and y would be used. A corner case that could happen is if I have z goes to xy and y doesn't have anything, so we remove it. Then z equals phi of x, which of course you don't need a phi function for that. So this can be replaced with z equals x. In fact, we can take all of the places where z occurs. So let's say we have a different place somewhere where z is used. I can replace that z with x. I can eliminate this statement as well and therefore eliminate this, etc. So every time I use a z, I can now use x instead. So I end up with v. So we can use these kinds of reasoning in order to optimize the code. Constant propagation can also be done in SSA form and can lead to further elimination of code. So if I have an assignment of some constant c to this variable v, then we can replace v with c for all the uses of v. So essentially we're taking that constant and using it everywhere that v was used. If I have a phi function with a bunch of arguments, in practice all of our phi functions really, because we're dealing with for loops and while loops, etc., they don't require very complex phi functions. They will be binary, but in the general case, you could have n different branches converging into one basic block, in which case you would have a n-ary phi function. And if all of these ci are equal to some constant c, then I can just replace that phi function with the constant. So I guess in this case, I'm eliminating the phi function by doing constant folding and constant propagation. Let's take a concrete example to understand how we can do code optimization using all of the different techniques we just looked at in this video lecture in order to optimize this piece of intermediate code. So this is SSA form that we've used before. We've used this example before. In fact, we use this as an example of how we can use a dominance frontier algorithm in order to insert phi functions and create SSA form. And now we're going to take the SSA form and optimize it, eliminate any redundant instructions and so on after doing constant propagation. So the main question we want to ask is, what is happening in this if statement? If we have a J2 value, so we know that if I go into this statement, into this basic block, then J3 is going to be equal to I1. I1 is a value of 1, right? I1 is always going to be 1. 1. So if I go into this branch over here, into this basic block 5, J3 is going to be assigned to 1. When I'm coming into this basic block number 7, I'm going to be using J3 and not J5 because I came through basic block 5. I'm using this path. So J4 will also be set to 1, and in this case J4 would be set to 1, so J2 would be set to 1, and then this would always be 1. So that's one possibility. In one possibility, if J2 is always going to be 1, then I will always go into this branch. This branch will always ensure that the value of J2 will actually be 1 every time. If I go into 5, then J2 will be locked at the value of 1. On the other hand, if I go into this branch, J5 will be equal to K2, and then the value of K2 gets added by 1 to K5. And at this point, K5 gets assigned to K4, and then I take K4 and assign it to K2. What happens here is K2 gets incremented by 1 again. So if I take this branch, then what's going to happen is J2 eventually will be increasing and not staying at 1, and then J2 will eventually be greater than or equal to 20, and therefore will always go through this branch. So the question is, if it's going through 6, it's going to ensure that eventually it will go through 6 again. On the other hand, if we always go through 5, then the value of J will not change. By using a simple kind of data flow analysis and just using constant propagation really in SSA form, we can figure out which of these is going to be the case. I suspect you already know, given that you can look at this program holistically. You can see which branch is likely to be the right answer. Like it's going to always go through one path through this program, and you know what that is, but we're going to mechanically do that step by step by doing various code optimization steps. Each code optimization steps will be quite local. So we want to figure out which will happen, which of these cases will happen. And then using SSA, we're going to find the answer. So let's start by doing some constant propagation. So we always look for cases where we are just assigning a value and not doing any real work. So we're just taking the value of K2 and assigning it to J5. J5 is then used over here. So what we can do is replace that value J5 with K2, right? So what I've done is, since J5 is always going to have a value K2, I'm just going to replace this J5 over here and replace it with K2. Now the next step is to realize that this value J3 is always going to be equal to 1. The value of J3 is a constant 1, so I can propagate that constant in here. Now the next thing I can realize is if I look at K3 and K5, what are these two statements doing? Well, they're both being given the value K2 plus 1. So it's a common sub-expression, K2 plus 1, that's common to both of these. I don't really need this basic block in order to compute a value for K5, because wherever I can use K5, I can instead use K3. I can actually here, instead of using K5, I can use K3. And phi function of K3 comma K3 is just the same as just using phi of K3. So notice that K2 in this case is going to be the value of K4. Right? So this K2 is never going to happen because if I eliminate this branch, then this is never going to occur. It's always going to be coming in from this side. So therefore, only this one will get selected. So I can get rid of this. So essentially what I'm doing is getting rid of this basic block altogether. And as a result, I end up with phi of 1 and phi of K3. And that's what I have here. Now the next step is to look at J4. And now we know that J4 is going to be equal to 1. And look at J4 over here and replace it with that constant, right? So J4 gets replaced with 1. It's just constant propagation. And now I have J2, which is also now equal to the constant 1. So in this case, J2 is the constant 1. Then this J2 is always going to be the constant 1. So this is going to get replaced with that constant. So it's 1 less than 20. Notice that always means that it's going to take this branch anyway. this branch is missing. There's no reason to take the false branch because 1 is always going to be less than 20. So by eliminating that branch, we already had eliminated that basic block, right? So instead of it coming over here, this entire branch can be ruled out, and we can say this is not going to happen. It's always going to be 1 less than 20, and it's always going to go this way. So that conditional is always going to be true. As a result, we can make this control flow a lot simpler by eliminating that branch. The next step is to get rid of this basic block. We also get rid of these I1, J1, K1 because they are not being used anymore. So they are redundant. We have defined them, but they're not getting used anywhere else in the code. So we can remove this basic block. We can remove these statements. Now we have reduced it to its very basic form. It's checking K2. It's getting either K4 or 0. The initialization was to 0. So it gets 0 if it comes from here. It gets K4 if it comes from here. And now it checks if K2 is less than 100. If it is, it goes to this and here to this and then comes back up. If K2 is greater than or equal to 100, it goes to the return. So as you can see, we can simplify this further. We can say that instead of K3 is equal to K2 plus 1 and then K4 is phi of K3, we can combine these two statements together and just call this K3 is equal to K2 plus 1 and then use that K3 as the input to this phi function. So notice that so far we've simplified it into this loop where K2 is incremented and we check this conditional statement. In the end, you might think, well, why not just eliminate that as well? Because all it seems to be doing is counting to 100 and then returning 1. But as we said about correctness, you might actually be using this function, for example, relying on it to count to 100 because you're sleeping for a fraction of a second before you call out again to some external service or something. So it could be relevant that it counts to 100 and we don't want to change that behavior. On the other hand, we made the exact thing that this program computes all the way from the initial. So if you start off with this initial SSA form, you can see that gradually we can reduce it down to exactly the instructions that are needed to be computed. And essentially we can see it is just counting to 100 and then returning 1. There are various other optimizations one can do with SSA that's outside of the scope of this course, which is dealing with arrays, pointers, and memory. So for more complex programs, we need dependencies, like how does one statement depend on another statement? And for memory locations, for example, we often have to model what happens when you read after a write. So if A defines a variable, V writes it, then B uses it, we want to make sure that that ordering is preserved. That dependency is important. If you have a write after write, then if A defines a variable and writes it, and then B is another statement that defines a variable and rewrites it, then it also matters which one is written second. And you can't reorder this because it might affect the correctness. And then you can have a write after a read. You have to make sure that if you're writing something after a read, you want to make sure that the write happens after the read. Otherwise, A, which is using a variable, might end up having the wrong value. Another kind of dependency is control dependency, where, if you're computing an expression and that expression is a Boolean expression, it could control whether or not another statement executes. So there is a dependency sometimes between statements based on the value that you compute. There are various types of memory dependence. So if you're storing a value in an array, for example, you might store 4 into an array at location I. You might retrieve something from location J and then write something to location K that is a value. Now, in this case, we can't tell if I, J, and K are all the same value or not. Sometimes you can, like if you're doing constant propagation, but sometimes they're function parameters and you may not be able to figure out what those values are unless you do whole program analysis. So these kinds of issues make optimization difficult. So there are similar problems with control dependence as well. SSA doesn't offer an easy solution to these problems, so you have to fall back on more data flow analysis kind of techniques in order to deal with them. There is an excellent book that gathers together a lot of the work, modern algorithms that are used for code optimization, is the Munchnick book, which is kind of the Bible of advanced compiler design, mainly for code optimization. And it covers a lot of these techniques that are needed for code optimization in a modern compiler for a fully specified programming language like C++ or Rust or any of these general purpose programming languages. As you can see, there are a lot of topics. We have covered very briefly some of these topics, but by no means can we cover all of them in this course. So this would be a good topic to follow up on if you're interested in code optimization. I highly recommend picking up this book and taking a look at it. Finally, I want to leave you in terms of code optimization with Amdahl's law, which tells you even if you're doing a good job at speeding up your code, that doesn't mean that your code will actually run all that faster. The idea behind Amdahl's law is fairly simple. So let's call this part P, which is the portion of the program that you can optimize. So P is the part of the program that you can optimize, and the speed up that you have, let's call it S for short, is the speed up you can obtain on that optimized part. Obviously, you cannot optimize every single instruction in your program. You can only optimize certain part of your program. And the question is, if you optimize that part of the program, how much of a impact do you expect to see in the overall running of the program? So the idea is fairly simple. This equation is derived in a very simple way. So let's take the total time. So P is a percentage of your program. So 1 minus P is the percent of the program between 0 and so we are dividing by 100. So it's always between 0 and 1. The part that is not optimized is 1 minus P. And that's 1 minus P of the total time. Plus you take P, which is the part that you can optimize, and you divide it by the speed up. And this is the part which is going to help you. Code optimization is going to speed up your program by that much. So this is the total time that you can get, which is the part that you couldn't optimize, which is here, and then the part that you could optimize, which is here. And you add those two up. If I take this as the theoretical execution time, it can be simplified further and we can calculate what is the speed up that I can get. Well, the speed up I can get is going to be T, which is the total time, and let's call this TS, which is the speed up time. And this would be, if I take this and I simplify it, it ends up being 1 over 1 minus P plus P over S, and which is exactly the equation that I've written here. This tells us what is my speed up, right? So this S here stands for my speed up. So for example, let's say that 30% of your execution time can be improved. Let's say that P is equal to 0.3. So 30% of your program can be improved in execution. And let's say that we in fact get a very good speed up, like we can speed it up by twice as much by doing code optimization. Well, this equation tells us the actual speed up will be 1 minus 0.3 plus 0.3 divided by 2, which is equal to 1.18. Overall speed up, you might expect a speed up of twice as much, but actually the speed up that you will get is just a little bit more, 20% more than your existing program execution time. So don't get your hopes up that code optimization will have a huge impact, especially if your percentage of the code that is optimized is not that much, right? It depends a lot. So what we want to do is optimize the common case. This is the 90-10 rule. Always pick the innermost loop that is executed a lot and optimize that. That's going to give you a better result. It requires a quantitative approach rather than a theoretical approach. So you need to do profiling, you need to do benchmarking, and this will tell us which part of the program needs to be optimized. And this is, I guess, common sense as well, but Amdahl's law really puts a number on how much improvement you will get unless you do a careful job of profiling and benchmarking. One usual problem is that the compiler writer is typically writing programs that are general purpose and don't know the application. If you do know the application, let's say it's linear algebra heavy, then often we can optimize that code a lot better if we know we are going to be writing matrix multiplication loops. Then we can optimize the hell out of that and do a really good job of it. So in summary, optimizations can improve speed and maintain correctness, and maintaining correctness is quite important. There are many types of local optimizations that we studied. We looked at static single assignment form and how we can do optimization using static single assignment form and how powerful that was in terms of code optimization.